Hello from Logan, Utah. We are Utah State University's Mars Rover team. Since September of 2024, our team of undergraduate engineering students has built on previous year's work to design and build this year's rover, Sophia. Here we present our system acceptance review to show our plans for success in the 2025 University Rover Challenge.
The rover uses a spider bogie style suspension, largely developed by last year's rover team. Our team modified the frame to decrease the rover's width and to lower its weight. This suspension allows for a wide range of articulating motion, allowing the rover to drive over difficult terrain. The wheelbase is comprised of low-pressure polyurethane tires for traction and stability. Tank turning allows the rover to make zero-point turns with simple control.
The communication system consists of an NVIDIA Jetson Xavier to execute control scripts, an Arduino Mega that parses scripts into operating signals, and two Ubiquiti bullet transmitters with omnidirectional antennas to establish a private Wi-Fi network between the rover and the ground station. One 22,000 mAh battery powers the wheel motors, the servos of the robotic arm, and the science module, and an 11,000 mAh battery powers the communications and control system. The comm system uses a publisher-subscriber system through ROS packages to pass control instructions to the rover. Simultaneously, the rover will capture video using Python's OpenCV library and send it over a WebSocket to the ground station. Both batteries are projected to last a minimum of 1.4 hours.
The communication system can transmit commands and high-quality video at ranges up to 500 meters. We can improve communication at higher ranges by compressing our video feed and by using our drone.
Our drone carries a camera and a third Ubiquiti bullet to act as a radio repeater between the rover and ground station. The drone's purpose is to improve transmission quality when the rover is over 500 meters away or when the rover travels out of line of sight. The drone may also be valuable for finding points of interest from above.
We estimate the drone's 13,000 mAh battery gives 10 minutes of flight.
To make the most of this time, the drone will remain parked at the ground station until needed. At this point, it will automatically lift off and fly to the rover's location based on the rover's GNSS coordinates.
The rover uses a Gearworks arm with a modified Lynx motion gripper to flip switches, open hatches, push keys, operate a joystick, and pick up and carry objects up to 5 kilograms. Control of the arm is accomplished by the use of a servo controller to feed PWM signals to each of its 6 degrees of freedom. The robotic arm module can be removed by unscrewing the mount to make space for the science module's linear actuator and auger.
The rover's autonomous capabilities use several USB webcams and the OpenCV library for analysis, which includes a 6x6 Orico tag detection library. We alter the camera feed to be grayscaled, and our code records and marks the tag's ID. We plan to autonomously type using a similar object detection method. After we pass in a code of up to 6 characters, the Jetson will use a video feed of the keyboard to locate the necessary characters. These will be passed as a location into the arm, and inverse kinematics will be used to move the arm to its new position. For autonomous traversal, the rover will use the current and final GNSS coordinates to create an initial path. This path will be modified using known geographical and elevation data of the operational area and real-time data from the camera's obstacle detection. An LED tower will be used to indicate the status of the rover. Solid red for autonomous operation, solid blue for manual or teleoperational control, and flashing green to indicate the rover made it to its destination. A red e-stop on the top of the electronics enclosure can be accessed in an emergency, cutting power from both batteries.
Our science payload is designed to collect, process, and analyze subsurface soil samples to assess habitability and search for signs of life. The system consists of a custom auger with an internal storage compartment, a sample carousel, a testing chamber, and a suite of environmental sensors for data collection and analysis. The process begins with the auger being lowered using a linear actuator with a 12-inch stroke. As it drills, the surface material is expelled through a chute, preventing contamination. Once the auger reaches a 10-centimeter depth, a small internal door opens, allowing deeper soil to enter a sealed container within the auger's internal compartment to be presented to the URC judges. At the same time, additional soil remains on the auger blades for in-site testing. Once the sample is collected, the auger is raised to align with the sample carousel, where the soil is deposited for chemical analysis. The testing chamber performs 2 chemical analyses to detect biological activity. A luciferin-luciferase reaction performed in a darkroom, where a light sensor records luminescence, indicating biological material, and a hydrogen peroxide catalase reaction, which detects organic compounds through a bubbling or foaming reaction, captured using an onboard camera system. Environmental sensors measure humidity and temperature to assess the area's habitability and potential water presence. All sensor data, test results, and sample conditions are displayed in real time, and data is logged for later review and comparison. A camera located on the auger mount takes close-up images of sample sites.
Thank you from the rover team at Utah State University. We're excited to show you what our rover is capable of. We hope to join you at the Mars Desert Research Station.